Okay, to prove that analytic functions are locally equal to their power series expansions, we'll first have to, of course, work out the various definitions that are underlying, such as sequences and series. But at the end of this presentation, we'll stand the result that every analytic function locally is equal to a power series. And that will make a lot of things easier because, as it turns out, and as you probably also recall from calculus, power series essentially function like infinite polynomials, and that means except for the infinite part, which of course we have to keep dealing with, but except for that, they are among the easiest to handle functions. And easiest in an advanced class has to be understood as easier than others, not necessarily as easy in the sense that all the work is going to terminate very quickly. Some of the computations we'll go through, in fact, will be rather epic in the later presentations, but they are still preferable to the alternative of not being able to solve the problem at all. As I often say in classes like these, the beauty isn't necessarily that things go quickly and easily. The beauty is in the fact that we can do it at all. Okay, we will show in this presentation that every analytic function is locally equal to a power series, as I mentioned, and that is its Taylor series. And that will simplify a lot of later results, and again, simplify in the sense that it makes a lot of things possible, not in the sense that computations necessarily only take 2 or 3 lines. And this simplification is one of the reasons why complex analysis is so powerful, and that's just that the analytic functions are just very well behaved. Okay, in order to understand power series, we've got to understand series. In order to understand series, we've got to understand sequences. And so that's where we're going to start. But we're not going to spend excessive amounts of time on what, well, I'm not sure if minutia is the appropriate word here. There's an awful lot of stuff that we can say about sequences and series. Some of it will just refer to your calculus class 4, and the main thing that we want to do here is we want to get the basics down so that we can get to power series, which is an approach that a lot of applied people take, because even though there is an awful lot of neat abstract and theoretical mathematics that you can done with sequences and series, the applications typically sit with the power series expansions. So the goal is to get the power series expansion of analytic functions as efficiently as possible. And we start with sequences. And a complex number L is called the limit of the sequence Z1, Z2, and so on of complex numbers. So a sequence of complex numbers is just a bunch of complex numbers indexed by the natural numbers. Technically speaking, that means a sequence is a function from the natural numbers into the complex plane. That makes sequences a clean mathematical entity, but people don't think of them that way. People think of them as this kind of progression. And L is the limit if and only if, for every epsilon greater than 0, there is a natural number n, so that for all n greater or equal capital N, we have that Zn minus L smaller than epsilon. Think back to the definition of the limit of a function. It was the same kind of situation. We were talking about every epsilon greater than 0, and for every epsilon greater than 0, there had to be a threshold, which in this case was delta, because the inputs were complex numbers. Well, this time it's a capital N because the inputs are natural numbers, so that for everything below or beyond that threshold, which in this case would be for all the large n's, just like for limits of functions it was z minus c0 smaller than delta, we have that the distance between the value and the limit is smaller than epsilon. So this is built after exactly the same scheme as the limit of a function at a point. And in this case, we then also write that the limit as n goes to infinity of Zn is equal to L. And the visualization is that a sequence really typically is visualized as a bunch of points that just try to move somewhere, and if this thing is convergent, if this thing has a limit, then ultimately these points just start clustering and coagulating around the L, and nothing is going to jump away from the L for large indices anymore. Okay, if we have that L has a real part Lx and an imaginary part Ly, and if we're looking at a sequence with real parts xn and yn, then the limit of Zn is equal to L if and only if the limit of the real parts is Lx and the limit of the imaginary parts is Ly. That seems to make a lot of sense. Everything up to this point, continuity, differentiation, and integration, worked component-wise, so certainly limits of sequences shouldn't work any different. And the proof is also not that bad, I think. We let epsilon be greater than 0. And if the limit of the Zns is L, well, then there is an integer n, so that for all n greater or equal capital N, we have Zn minus L is smaller than epsilon. But then for all n greater or equal capital N, we have that Xn minus Lx absolute value, which is smaller than Zn minus L absolute value, is smaller than epsilon. And, well, of course, similarly, we also have that the Xn, the Yn minus Ly is smaller than Zn minus L is smaller than epsilon, and that means that the Xn's goes to Lx and the Yn's goes to Ly. Conversely, if the limit of the Xn's is Lx and the limit of the Yn's is Ly, well, then there is an integer n, so that for all n greater or equal capital N, we have that Xn minus Lx is smaller than epsilon halves, and Yn minus Ly is smaller epsilon halves. Remember, these epsilon proofs, sometimes you have to make choices so that things work out pretty near the end. We know we can do that, and we'll see where the half comes from in just a minute. Well, then for all n greater or equal than n, we have Zn minus L absolute value is Xn plus Iyn minus Lx plus Ly absolute value. And now we just sort real and imaginary parts. And so this is Xn minus Lx plus I times Yn minus Ly. And if we use the triangular inequality, we get that this is less than or equal than Xn minus Lx absolute value plus Yn minus Ly absolute value. And the first one is smaller than epsilon halves, the second is smaller than epsilon halves, and that means that the limit of the Zn's is equal to L. Notice that this is certainly a rather abbreviated proof. We are now certainly also nearing the stage where we have seen enough of these proofs that we ought to be able to fill in a few more details that go from the definition to saying that the limit is L and so on, and so I've chosen here to make this one a bit quicker. That means it's going to be a bit harder to digest, but the more of this stuff you can do mentally, the easier it becomes, and that's, of course, the ultimate goal. As an example, let's take the limit as n goes to infinity of 1 over n plus I times n squared plus 1 over n squared, and I claim that that limit is I. And that's fairly easy because I take that limit, that's the limit of the real parts, plus I times the limit of the imaginary parts. Well, the real part is still 1 over n, the imaginary part is 1 plus 1 over n squared, and that goes to 0 plus I times 1, which is I, just as claimed. Also, another example here, for z absolute value smaller than 1, we have that the limit as n goes to infinity, z to the n over 1 minus z is 0. Well, that sort of looks like it's obvious, because when z absolute value is smaller than 1, then z to the n goes to 0, and then that means this is something that goes to 0 divided by something that stays away from 0. But we don't have those technical tools yet, even though we could choose to put them in place. But we can also work this out directly, and it's a good exercise in working with complex numbers. Basically, we need to reduce all this to limits for real numbers. So let's see how we do this. We take the limit of z to the n over 1 minus z. And first thing we do is we expand with 1 minus z bar to get a real number in the denominator. And then we go to the polar form. So z to the n is r to the n e to the I n theta. And then z bar is r times e to the negative I theta. And everything else stays the same, because 1 minus z absolute value squared, that's going to be just a real number. Now we work that out, and that's r to the n cosine n theta plus I sine n theta times 1 minus r cosine theta plus ir sine theta, and that's because cosine minus theta is cosine theta, and sine negative theta is negative sine theta, and then the minus becomes a plus for the sine function at least. And, well, that still has imaginary parts and real parts mixed, so now we multiply this out. First find the real part, which is r to the n over 1 minus z absolute value squared is kept, then we have cosine n theta times 1 minus r cosine theta, that's this term, and then we have I, which is minus, and we have a sine n theta times r sine theta, and that's what we have down here. And for the imaginary parts, well, we keep the I on the outside, we have r to the n over 1 minus z squared still with us, and the imaginary part now is cosine n theta times r sine theta, and then sine n theta 1 minus r cosine theta. And that limit now very much collapses to 0, because what do we have here? Now we can use what we know about real numbers. And we have that the cosine is bounded by 1, this is bounded by 2, this is bounded by 1, so this is all just bounded by 3, and then so 3 over 1 minus z absolute value squared, multiplied by r to the n, but r is z absolute value, which is smaller than 1, and we know for real numbers, r to the n goes to 0 as n goes to infinity if r is between 0 and 1. Same argument applied to the imaginary part, gives us 0 for the imaginary part, and therefore 0 overall. Now let's talk about series. In infinite series, z1 plus z2 plus z3 and so on, basically just adding numbers indefinitely, and basically the substitute for adding numbers indefinitely, which we set equal to the sum n equals 1 to infinity zn of complex numbers, is set to converge to a limit L if and only if the sequence of the partial sums, which is just the sum n equals 1 to capital N zn, so z1 plus z2 plus all the way to z capital N, converges to L. In this case, we also write that the sum is equal to L, the infinite sum, and we note here that the symbol that has the infinite sum stands for the series as well as for its value. And we also note that technically we really haven't defined what a series is, and that is very common. I've looked for that quite a bit, and I have yet to find a text where people say such and such is a series. I think the closest could be that implicitly we realize here that this thing is essentially a sequence of partial sums, but that becomes very unhandy, and really we want to think of series as infinite sums. It's just that technically speaking, these things will always be limits of partial sums. Okay, so if we have that our L is Lx plus ILy and Zn is Xn plus Iyn, then the sum of the Zn's is L if and only if the sum of the Xn's is Lx and the sum of the Yn's is Ly. That looks just like the first result on sequences, and in fact it is, because if we let capital Zn be a partial sum of the Zn's, if we let capital Xn be the partial sum up to capital N of the Xn's, and if we let capital Yn be the partial sum of the Yn's up to capital N, well, then we just apply the earlier theorem on sequences to the sequences denoted with the capital letters, and it turns out, because this, well, this sum here is the limit of the z sub n's as capital N goes to infinity, because the x sub n's, the limit of the x sub n's is this sum, and the limit of the y sub n's is this sum. It turns out that that theorem applies directly. Okay. If a series of complex numbers converges, then the limit of the terms must be 0. That is, limit of the Zn's itself is equal to 0. We have to be very careful here. As soon as we talk about series, on one hand we have the limit of the partial sums floating around, but we also have the limit of the terms floating around, and the two are not the same. Now, convergence implies that the terms go to 0. That's a quick proof, actually, because if we let L be the limit of the partial sums of the Zn's and epsilon is greater than 0, well, then there is an integer capital N, so that for all k greater or equal capital N, we have that L minus the sum n equals 1 to k minus 1 of the Zn's is smaller than epsilon over 2. Which means that for all k greater or equal than n, we have that zk absolute value, which is just the difference between the absolute value of the difference of the kth partial sum and the k minus first partial sum. Then we just do the one trick there is in mathematics, right? We add 0. We have a minus L here, and then we have a minus L here, so those two are still the same. Now we use the triangular inequality, so this should be less than or equal. And now it is less than or equal. Well, and now we realize that this difference here, because of the way we chose our cutoff, this is less than epsilon halves, and the other one is less than epsilon halves also. And that means that's epsilon, and, well, that means that the zk's go to 0, because the definition of the limit of the zk's being 0 is that for every epsilon greater than 0, there is an integer n, so that for all k greater or equal than n, we have that zk absolute value is smaller than epsilon. Okay. Note, and this is the part that in calculus is often done wrong, and because we're not doing too much, it's not that critical there, to at least for passing the class. Of course, you never want to have a wrong knowledge remembered or so, but the converse is not true, meaning the terms can go to 0, but a series may still not converge. And the standard example is the harmonic series, the sum n equals 1 to infinity 1 over n, which is 1 plus 1 half, plus 1 third, plus 1 fourth, plus 1 fifth, plus 1 sixth, plus 1 seventh, plus 1 eighth, plus 1 ninth, 1 tenth, and so on all the way through 1 16th. And then, of course, it continues like that, and the reason why I've broken that up so strangely is because, well, 1 plus 1 half, 1 is greater than 1 half, 1 half is greater than 1 half, 1 fourth plus 1 third is greater than 1 half, because 1 third is greater than 1 fourth, right? 1 eighth, this was greater than 1 eighth, greater than 1 eighth, greater than 1 eighth, so these four terms add up to something that's greater than 1 half. Here's 1 16th, greater than 1 16th, greater than 1 16th, all the way through. These 8 terms also add up to 1 half, and so that means that this sum is greater or equal than 1 plus 1 half plus another 1 half plus another 1 half plus another 1 half, and we can keep going like that, just taking longer and longer chunks, but no matter how far we go, we will always find a chunk that has size at least 1 half, and so that means that this sum is infinite, as we also say in slightly informal parlance there. Okay, so a series of complex numbers is now said to converge absolutely if and only if the sum of the absolute values converges. And that's a really neat notion when it works, because absolute convergence strips everything away that is hard about complex numbers and reduces everything to a series of non-negative numbers, which hopefully will be easier to handle. Unfortunately, not every convergence series is absolutely convergent, and we can take a look at that with this sequence here. -1 to the n plus 1, that just means that your signs are alternating, divided by the ceiling of n halves. So that's you divide n by 2 and then round up. That gives you that your first term is 1, your next term is -1. The next term is 1 half, the one after that is -1 half. The next one after that is 1 third, the next one after that is -1 third, and so on. And if you do that, this does converge to 0, but be careful, this is now not an algebraic equality. This talks about the limit. But then on the other hand, if I take the absolute values, then that's the sum of 1 over n halves ceiling, which would be that's 1 plus 1 plus 1 half plus 1 half plus 1 third plus 1 third, and so on. So that would be larger than the sum 1 over n, which diverges, which goes to infinity, so this thing is also infinite. Okay, so that means, again, we have tools, we have ways to make things potentially easier, but we have to make sure that these tools, that we're allowed to apply these tools. Okay, so if the series of complex numbers converges absolutely, then it converges. So even though convergence doesn't apply absolute convergence, at least when we've got absolute convergence, we will have convergence. So the vocabulary makes sense. Converges absolutely sounds stronger than convergence, and it is. And the proof is, well, you take your function and it's your terms, and there's zn equals xn plus iyn. We know xn absolute value is smaller or equal zn, and yn absolute value is smaller or equal than zn, which means if the sum of the zn's converges absolutely, then by the comparison test for series of real numbers, check back on your calculus text, that means that the xn, the sum of the xn and the sum of the yn's converge absolutely. And that means, because of what we know about series of real numbers, that the xn and yn converge, and now by the first result we had on series, as we split things up into real and imaginary part, if these guys converge, then the series of the complex numbers converges to. Okay, now a couple of examples, or at least one very important example, and that's the geometric series. For every complex number q with q absolute value smaller than 1, we have that the sum n equals 0 to infinity q to the n is 1 over 1 minus q. Okay, so let's take that sum, and we know that that's the limit of the partial sums, where we go only up to capital N. Well, that, because we have the geometric series formula, that's the limit as n goes to infinity 1 minus q to the n plus 1 over 1 minus q. I think we've proved that by induction at some point in time, but it's also a standard formula that can be found, including its proof, in a variety of references. And we know now, well, that was something that we did earlier in the presentation, q to the n plus 1 over 1 minus q, that went to 0, right? So this is actually 1 minus 0 over 1 minus q, and that's 1 over 1 minus q. Okay. We also want to be able to split this apart, and for every complex number q with q absolute value smaller than 1, we have that the sum n equals 0 to q to the n equals 0 to infinity q to the n is the sum n equals 0 to capital N q to the n plus q to the n plus 1 times 1 over 1 minus q, and that's just messing with sums. We take the infinite sum, we realize that that's a limit of partial sums. Now realize that the partial sums, because we're going to break it up at a capital N, we use capital M as our dummy index here. Now we break the sum up, because of course the finite sum can be broken up at N. The fact that M has to be large enough is not a problem, because we are only interested in what happens when M goes to infinity. And well, so we break it up like this, and that's of course the sum is its own limit, because that doesn't depend on M, and the rest is the limit as M goes to infinity of this stuff here, and I can pull a q to the n plus 1 out, and if I do that, I'm left with an exponent n minus n plus 1. Now I just shift the indices, so this is still the sum n equals 0 to capital N q to the n, still the limit, still the q to the n plus 1, but now if I set k equal to n minus capital N plus 1, then k starts at 0, ends at capital M minus n plus 1, and we have a q to the k as the exponent, and the limit of that as m goes to infinity. Well, this thing here still goes to 1 over 1 minus q, and, well, first of all, I can just say, because n goes to infinity, m minus n plus 1 goes to infinity, so we get the infinity up here, and that's then the sum of the q to the n plus q to the n plus 1, 1 over 1 minus q. Alright, now we're finally into the Taylor series expansion, so here's where all this stuff is going to pay off. We take a function that is analytic on a disk z minus z0 smaller than some radius r. And then there is a sequence an of complex numbers, so that for every z in the disk we have that f of z is equal to the sum n equals 0 to infinity an z minus z0 to the n. And it turns out that the an actually is the nth derivative of f at z0 divided by n factorial. Well, let's take a look at this. Here's z0, here is z, and the whole thing is inside a big disk of radius r. What we're going to do now is we are going to integrate on a slightly smaller disk of radius lowercase r, and the points on that smaller disk will be c. So let that be the circle of radius capital R around z0 oriented positively. And I'll need to get back here. Okay, we're back. Turns out what I had to change was I have to make sure that f is analytic on a disk z minus z0 being smaller or equal than r, which actually means it's analytic slightly beyond that disk. But that way I'll actually be able to integrate on that circle, which is what I want to do in the next step. If the function had only been analytic on the open disk, then I wouldn't have been sure if I could apply the Cauchy theorem on the perimeter on that circle, and that's of course what I want to do here. So let's take a look at this. Take the circle around z0 of radius r oriented positively, and we know by the Cauchy integral formula that f of z for any z inside that circle is 1 over 2 pi I integral over the circle f of c divided by c minus z d c. So c are those points on the circle. Well, that, now we just add 0, right? This is the same formula except that I've subtracted z0, and then minus minus, I've added the z0 again. And now we do some more algebra. We try to involve geometric series, right? So from here to here, I kept the 1 over 2 pi I, the integral of the f of c and all that. I factored out a c minus z0, and if I do that at the beginning, I get a 1. And for this, I just get z minus z0 over c minus z0. So this looks like 1 over 1 minus q, and because z is closer to z0 than c is, this q has absolute value smaller than 1. Which means that this now is the integral. Again, we keep the front the same. This is the integral. This is 1 over 2 pi I integral over the circle f of c divided by c minus c0 times. And we know that this thing, by just the result, the example that we just had, is the sum n equals 0 to capital N z minus z0 to the n over c minus z0 to the n, plus the sum n equals n plus 1 to infinity z minus z0 over c minus z0 to the n dc, because this thing here is the infinite sum of this, the powers of this fraction. And that is the sum n equals 0 to capital N z minus z0 to the n 1 over 2 pi I integral of this stuff here of f of c divided by c minus c0 to the n plus 1. That's just the first sum where we pulled out the z minus c0 to the n to come here, and the c minus c0 to the n with the c minus c0 here becomes c minus c0 to the n plus 1. And then we have, in addition to that, 1 over 2 pi I f of c divided by c minus c0. That's just kept as is, and we know that this sum from the preceding computation, or from a computation similar to that, is z minus c0 over c minus c0 to the n plus 1, because we can just factor that out, times 1 over 1 minus z minus c0 over c minus c0 again. And basically now, if we can show that as n goes to infinity, this term back here goes to 0, then this becomes the power series representation, because this is z minus z0 to the n, and the an will be this thing. Okay, so on the next panel, we're just going to show that that last term goes to 0. Because z is fixed, and z minus z0 is smaller than r, which is c minus c0, for all c on the circle, we have that there is an r smaller than 1, so that z minus c0 over c minus c0 absolute value is smaller than r for everything on that circle. And that means that this ugly integral we've had at the back, if we pull the absolute values in, and again the dc absolute value is just that we integrate against the length essentially, we get the absolute value on the inside. And we realize that the absolute value of z minus z0 over c minus z0 to the n plus 1, well, that's just less than or equal than r to the n plus 1, right? So that comes out, and everything else still stays the same. But this stuff here doesn't depend on n. This is just an integral of a function that in fact is never equal to 0. So that's an integral of an analytic function. Well, okay, except... well, that is, okay, it's an absolute value of an analytic function, but it is a well-defined integral. It is a number. And so that means that if we have r to the n plus 1 times a number, that will go to 0 as n goes to infinity, because r is smaller than 1. And so that means that f of z is actually that infinite sum, but this is just the sum copied from 2 panels ago with the capital N replaced with infinity. And we realize now that these guys are the a sub n's, and from Cauchy's integral formula we know that this is the nth derivative of f at z0 divided by n factorial, because the expansion of Cauchy's integral formula said that fn of z0 was n factorial times all this stuff. Okay, and that's the end for proving that every analytic function is equal to its power series expansion. Let's take a look at some examples. For example, for every complex number z, we have that e to the z is the sum n equals 0 to infinity z to the n over n factorial. Basically, for f of z equals e to the z, we have that the derivative is equal to e to the z. That means all derivatives are equal to f e to the z. and that means the nth derivative at 0 is 1 for all n, and that means the a sub n are 1 over n factorial. And because f of z equals e to the z is analytic on any disk around the origin, the expansion will be valid for all complex numbers, because for any complex number, I can find a disk around the origin that contains that complex number. Okay, for the cosine function, it becomes a little bit more complicated because the coefficients are more complicated. But how do we get those? Well, once more, the expansion is around the origin, right? Because z to the 2n is z minus 0 to the 2n. Because f of z is cosine z is analytic on any disk around the origin, whatever expansion we find will be valid for all complex numbers, because every complex number can be captured in one of those disks of radius r that the theorem talks about. And so now we note that if f of z is cosine z, f prime of z is negative sine z, f double prime is negative cosine z, f triple prime is sine z, f quadruple prime is cosine z, and after that it repeats, which means f of 0 is 1, f prime of 0 is 0, f double prime of 0 is negative 1, f triple prime of 0 is 0, just using the values of the sine and cosine, f quadruple prime of 0 is 1, and after that it repeats. So now we just have to find a pattern, and from this pattern we're seeing that the odd number terms are all 0, right? The first term is 0, the third term is 0, the fifth term is 0, and that's because the odd number terms are either plus or minus sine of z, which is 0 at 0. Okay, the even number terms we can now abbreviate as a2n, that way we automatically indicate that the index is even, and they are alternatingly positive or negative, and that can be encoded with a negative 1 to the n. We just have to make sure it starts the right way, but it does, because if we now say a2n is negative 1 to the n, that would be the derivative, and that makes sense because 2 times 0 is 0, so a0, the derivative there is negative 1 to the 0th, which is 1, and then at a2 it becomes negative 1, a4 it becomes plus 1, and so on. We divide by the factorial of the index, so we divide by 2n factorial, and that's what a sub n is supposed to be, and that's exactly what we had here. We just have to make sure that the index of the a is also the exponent of the z. Okay. Finally, I think at least finally, for all complex numbers with z absolute value smaller than 1, we have 1 over 1 minus z being the sum of z to the n. Well, that was an earlier example, so that's not the end of this one. Finally, we just want to take a look at an example that's sort of formulated like a homework problem. Find an expansion for f of z equals 1 over z plus z to the 4th for z absolute value smaller than 1. We will in the future be after these kinds of expansions quite a bit. So how do we find them? Well, 1 over z plus z to the 4th is 1 over z times 1 over 1 plus z cubed, and now we realize that's one of those 1 over 1 minus patterns. So this is, let me make that more detailed. And we're back. Well, I found a little mistake here, and that is, this is one of those 1 over 1 minus patterns, so the 1 over z stays the same. This is 1 over 1 minus negative z cubed, and that's actually a fairly standard trick to turn all sorts of expressions that are similar to this one into power series, because now we know this is 1 over 1 minus q, and so if I just replace q with the negative z cubed, I will get a valid expansion. So I get 1 over z times sum n equals 0 to infinity q to the n, where q is negative z cubed, and now we just work that out. That's 1 over z times the sum n equals 0 to infinity negative 1 to the n times z cubed to the n, which is z to the 3n. And then if we want to, we can push the 1 over z inside, so we get the sum n equals 0 to infinity negative 1 to the n z to the 3n minus 1. And you may notice here that, well, we've got a negative exponent in this power series expansion, and we will formally deal with negative exponents in these kinds of expansions, in fact, in the next presentation. But for now, practice expanding functions into power series using that Taylor series formula that we have derived. Work a little bit to get yourself familiar with sequences and series, and then we're going to continue with series with negative exponents, and after that we're already ready to reap some of the benefits and do some rather impressive computations actually that would not be possible otherwise. I'll see you there.